So today we're going to look at my calculus doing friends, and today we're going to look at 5.2. And so that's kind of our goal for today. And the topic is solids of revolution. And what they're looking at is if you have a solid and if you were trying to find the volume of it, and particularly things that are not like this stack of poker chips that I have here. It is a cylinder, and so here's my side of it. And so if you had something that's not perfect, I can use the formula for a cylinder to find the volume of that. But if I wanted to find the volume of something like this, where these things are all, they're not perfect, that's not a perfect cone and, you know, and whatnot. But what they do have in common is that when I slice these things, just like these poker chips, when I slice these poker chips up that we're making my cylinder, that each little piece, each little slice that I have on this too would be a circle. And in fact, it's a disc, and I want to slice it wafer thin. So these poker chips are sliced pretty thin, but I would like to even be a little bit thinner than this when I slice them. In fact, I'd like the thickness to approach 0, right? And so this piece, if I sliced it up, and so anyway, so that's the story. And then the idea is that you could find the volume by this slicing method by integrating. Remember, the integral sign adds up. And so you're going to be adding up the area of each piece, which is a circle, times the thickness. Dx is the thickness of each piece. And so the area of this times the thickness would give you the volume of it. And then I'm going to add up all those volumes. So I'm going to, you know, this was making up my piece. So add these together, and this one and this one, etc. And on something like this, they wouldn't all be the same size. So I would slice it wafer thin and be adding up the volumes of each little piece, but they wouldn't all be the same size. So that's kind of the idea on that. I'm going to show that I am a true boomer here. And my son caught me practicing to see if this would work. And he was like, he said something kind of derogatory, but not real bad. He said, "You're kidding me, right?" is what he said. And so let's see here. I guess I got this too big. Oh, I forgot to tell you about Professor Rob Bob, and I've given you a link for him. He does some really, really, really nice examples on YouTube, and so you can check him out. What I wanted to show you, though, was this. And, oh, I closed it. Darn it. Okay, so I got that copied. And I can come here. I had it open. Oh, maybe I still have it open. No, I think I've... Flash. No. There it is. Okay, so there it is still. And so I've given you the link for this, but this is something on Pearson's website, not Pearson website, Cengage's website, and it's a manipulative, and this one is just of a ball of a sphere, and of course the volume of a sphere is 4 pi over 3 if you have a sphere of radius 1, right? And so and so they say what that volume approximately is, and then they're showing you what the approximate volume is by using how many discs to slice it up. And so if I didn't use very many discs here, here is with just 4 discs, I believe. Then you can see that the approximation is more off, right? I mean, as far as the approximation is this, and so this is the error. But as I go to more and more discs and slice it, and then I'm finding the volume of each disc and then adding them together. So as I do that, so you can see it starting to look more and more like a more and more round. They have it all the way that you can do 40 And when you do that, your error is almost zero. And so that's kind of the idea. Anyway, so that's what we're going to be looking at and doing. And so we'll go through our notes here and see how we do. So like I said, I gave you so that if you wanted to give a try to that, you could. And okay, so the general idea here then on the solids of revolution is that we're going to take some function here and we're going to revolve it around an axis. And it doesn't necessarily have to be the x-axis, but it can be the x-axis. And when we do that, we get something that is like what I had here, right? And so by revolving it around the axis, I get something that when I slice it is going to have a whole bunch of cylinders, and I want to slice it really thin so that those cylinders are so that I could almost think about just the area, right? And so the idea then on finding the volume is that when you slice each piece here, so when I start slicing here and start cutting this, slicing it and making a little cut in it, and if I was able to pull that out like I did the poker chip, right, and show it to you, it would be it would be a circle. If I went here and I did that same slice, right, cut this one would be just bigger than that one was, right? And so the idea is that each of my slices would be a disc. I don't know if that's how you spell disc. And the volume of a disc is pi r squared times how thick it is, the thickness of the disc, right? And so that would be the volume. And so this is the area of the circle, and this is dx, how thick it is, right? And so, and then what you would do, here I've just drawn 2 discs is all I have, and the idea is to draw infinitely many discs between here and here, and then add them up, and that's what the integral does. It's an adder. The big S stands for sum. Add these things up. So anyway, so we'll go on and I'll show you the basic technique of doing these. So the basic technique for finding the volume is if you're rotating around the x-axis or something that's parallel to the x-axis. Things that are parallel to the x-axis look like this: y equals a constant. That's how they look when they're parallel to the x-axis. So like y equals 2 would be parallel to the x-axis. And so I would use this method here if the axis of rotation was y equals any constant. The x-axis, if you're wondering, what is the x-axis? Well, the x-axis is y equals 0 is what it is. So actually they all have that same story in this on this side. So what you do is you make sure that your equations are solved for y. Then you graph the equation and identify the region that's going to be revolved and kind of sketch it out. So that's what they've done here, is that they've graphed the equation. They said this is going to go from A to B, and they've kind of shaded that, and they said we're going to revolve it. And then they tried to draw a 3D figure of it, and you guys would laugh at my 3D figures, so I probably won't draw too many of them, and that's why I recommended Professor Rob Bob here, because you won't laugh at his 3D drawings. They're awesome. And so anyway, then what you want to do is you want to draw a typical radius, and I want you to note that the radius is perpendicular to the axis of rotation, and you want to write out what your radius equals. And so, and in fact, I want to tell you right here, I wish I had more time when I was editing these to write this in, so I'll write it here. R equals the distance from the axis of rotation which might be the x-axis and might not be the x-axis, right? So if it's y equals 0, then it's the x-axis, but y equals a constant is not the x-axis to the curve. Whereas y equals the distance from the x-axis to the curve. Sometimes r and y are equal to one another when we're at y is 0, right? When we're going around that x-axis, because it's if the axis of rotation is equal to this. And so, but always you'll be using your axis of rotation and your y to come up with what your r value is. And we're going to practice it, so don't worry. And then the formula, you're going to have your integral going from a to b. So here was our integral going from a to b, right, of our area. And since each times the thickness, and since each area is a circle, it's pi r squared times the thickness dx. Now, if you're wondering, and our book doesn't do it, but if you're wondering, hey, well, what if instead of making circular by rotating the way they did, what if they made squares, and this was all squares? Then would the formula somehow be side squared times the thickness? Because that's what the formula for the area of a square is, and the answer is yes, that's exactly right. And so on the other hand, if you're going around rotation around the y-axis or a line parallel to the y-axis, now the y-axis is x equals 0 is the equation for the y-axis, and a line parallel to the y-axis would look like x equals some constant. Then your equations need to be solved for x. You need to graph out, this got kind of messed up somehow in my editing. You need to graph the equations and sketch the region. You need to draw your typical R, and then your formula is going to be from A to B. Because I'm going around the y-axis, it's going to be dy, or something parallel to the y-axis. When I was going around the x-axis, it's going to be dx. And yeah, that's going to be important. And so we'll watch it. But it's nice. Same, right? X-axis, dx, right? Y-axis, dy. So we'll be able to remember. And our area, pi r squared. Now here, r is still the distance from the axis of rotation to the curve. But because we're going around a different axis, we're going to be interested in x. And x is the distance. So this is, I can give the same definition over here for r, but is the distance from the y-axis to the curve. Now these could be the same, right? But they're not always the same. And of course the first examples, they are going to be the same because they're going to start us off easy. So this is a problem that we're gonna check out and do, and so we'll look at it. We'll see how we do on it. I have to get my stuff out of my way, so I get so many things out of the way that I can't find my mouse because I want to get this. And to show you, I'm doing the ones from your book because I'm really not that good at drawing the 3D. And actually, you don't have to draw the 3D to be able to find out the volume. So I'm not good at drawing the 3D. I think that that my department should send me to a drawing school. Would be nice. But I'm okay at finding the volumes. And so here I got my computer up so that I can do it. And so the first thing that you want to do is it says y equals the square root of x. So you want to make a sketch of y equals the square root of x. So it would start here at x is 0 and look something like this. They also told us that y equals 0. Now y equals 0 is the x-axis, right? So here's y equals 0. And then x equals 1. So here's x equals 1. 1. And then this region that we just trapped is the region that we are going to rotate around the x-axis. So they're going to be rotating this around the x-axis. So I want to show you what that would look like. I just went to the place where I had the website that I showed you. And so here, if I can make it do the animation and rotate it. And so there is when it rotates it around the x-axis, right? And then it shows you a typical disc if they were to slice it. And you can move that. You could move that disc here. So you can move that disc. And so you can see that that disc gets smaller and larger as you go. And over here you can see this is in the 2 dimension. And here when I move the disc, you can see that, whoops, I was rotating that. Whoops, you have to move the disc down here, huh? And so when I move that disc, you can see the disc over here moving, right, as it goes along there. Okay. And so that's kind of the story on what we have. So some kind of a megaphone looking thing, right? And they're asking us to find the volume of that, and this is solid. And so we're gonna do that. You can go and play with the figure if you like. That's why I chose to do the examples out of the textbook so that we could look at those. So, so what I want to do is I want to draw it. I drew it, right? And you want to make sure, I'm going to use a disc here. And if you're going around the x-axis, you want to make sure, for my disc method, that this is going to be dx, right? And your equation, they said, needed to be solved for y, and it is solved for y. So if I'm going around the x-axis and I'm going to try to use a disc, it's going to be dx. And my equations need to be solved for the other variable. So this is my main equation. And then your radius goes from the axis of rotation, which just happens to be the x-axis, right? That makes it easier. And it goes to the curve. And so right there is my radius. And that value right there, from here to here, is called y. And so the distance from the x-axis to a curve is always called y. And so, and that happens to be what my radius is for this particular problem. So my radius is equal to y, but I want everything in terms of x. You see that on this? So what did that tell us about y? Y is equal to the square root of x. So that's what I'm going to use for my radius, the square root of x. So when I'm right here at 1, my radius is the square root of 1, which is 1. And when I'm here at, say, 1/4, I know I picked a nice value, right? Then my radius, when I'm here at 1/4, is the square root of 1/4, which is 1/2. So this height right here is my radius of my, it's the radius of my circle, right? Because when it, remember the radius is half the diameter, and when you imagine it, how they had it here, right, to get it all the way drawn out, the radius is just the distance from the axis of rotation here out to the one side. You could go it this way if you wanted to go that way with it, right? It doesn't matter, but of course I'm going to go positive because that's going to make it easier, and so that you can really look at that disc right there, right? So I'm just going straight to one of the sides. So the radius could be measured any which way, but it's just half. And so the way I've got it drawn, before I tried to look at the 3D-ness of it, right, was just the radius, and so it's so perfect. And then the formula right here for the volume is pi r squared, right? So the volume is the integral pi and then the square root of x squared dx. And then your integral's bounds will be, we're going to be drawing and figuring out all of these, each one of these, right? When we pull it and we look at it, we pull it off and we look at it as a circle, and this is a really tiny circle, right? And this is the bigger circle, right? The circles are all different sizes, and this one down here is a circle of size 0. And my circles are going to go from 0, from x is 0, they're actually discs because they have a little wafer thin thickness, all the way to 1, so 0 to 1. And then now I'm like ready to integrate this, and I'll find that volume, hot diggity dog. So the volume from integral here at pi x, the square root and the square undo one another, dx. And the pi, you just hold still, right? So pi, and then the antiderivative of x is x squared over 2. From 0 to 1 is going to be my volume. So when I plug in here, this is pi over 2 times 1 squared minus pi over 2 times 0 squared. So my volume is pi over 2. There. And so we did a lovely job on that. So that's kind of that first example. So here's a second example. Find the volume of the solid obtained by rotating the region bounded by the given curve about the specified line, this time the y-axis, it says. Sketch the region, the solid, and a typical disc or washer. So we'll give a try to it. So I have this equation, 2x equals y squared, and I have to draw that. That's the first thing to do, is to give a drawing on that. You can solve that for x, and so I think I might. It looks like it would be better if I solved for x, right? So x equals y squared over 2. So I know that's a parabola on its side, and I'm okay to just go and get a few points on it, like when y is 0, x is 0, and when y is 1, then x is half, and when y is 2, 2 squared is 4 over 2 is 2. And so I didn't get any of the symmetry points, but I'll put them on here. So 0, 0, and at half I'm at, so here's like 1, and at half I'm at 1. And also at, when y is negative 1, I would be at half as well, right? Half, negative 1 here. And then 2, 2. Oh, that's, my scale gets really bad. Probably should be taking a collection in the class for my drawing, for some drawing lessons for me. And for the same reason for some symmetry down here. Okay, so I've made a lovely drawing, and they said that x equals 0. Now x equals 0 is the y-axis, so here's x equals 0, and then they said y equals 4. So this was at a height y equals 2, so y equals 4, this thing is going to get big on me, huh? Is right up here precisely, so you didn't think that I would be drawing right through my words, but there I am. Drawing right through my words. Okay. And the area that I'm going to try to find, or the area that I'm going to rotate, is that's trapped by the 3 curves. So I was so carefully drawing the symmetry down here, and I didn't even need it, right? Because it's not part of what's being trapped. So this is one of the sides. This is one of the sides of the region that I'm bounding, and this is the other side here. And so this is actually what's going to get rotated. And this is going to get rotated around the y-axis. So it's going to go right here around the y-axis. So I've made a lovely sketch of it. If you wanted to sketch the solid, then it's going to come out over here, right? Is where it's going to come, and like that. as it goes. And I'm not very good at sketching the solid, but that's what it's going to look like, and you can kind of try to make it look rounded. Oh man, Pat Serpa can draw them really good. And so and then they wanted me to draw a typical disc, and so a typical disc in here is going to look like, and it's going to go here all the way over to here, right? And there's a typical disc that I would pull out. So this time, when I pull them out, they're rounded this way, and I'm going to show you a circle is what's going to happen. Okay, so when you're going around the y-axis, then if you're going to use a disc, it's going to be dy. And that means that your equation needs to be solved for the other variable, which means my equation needs to be solved for x. Well, kind of on a natural, I did that without realizing, and so that's hot diggity dog. And it's nice that I'm going around the y-axis, because when I do my radius is the distance from the axis of rotation to the curve. So there's my radius right there. But that happens to also be, remember what we said about that? Because it happens to be, it's coincidental. And if you're thinking, well, what if it's not? Well, don't worry, I'm going to tell you. The distance from the y-axis to the curve is called x, right? And that's what we have as our radius from the y-axis to the curve. And that's called, so our radius is called x. So, and the good news is, remember I want everything in terms of y. X is equal to y squared over 2. You get where you don't write this whole thing, but that's the thought on it. That distance is always called, that distance is called x, right? And so my formula, remember, is pi r squared. This is my volume, and my volume is going to be the integral pi, and then this is y squared over 2 squared dy. And now all I have to do is get the bounds, and I've got this kind of messy looking. Now this was y equals 4 up there, right? And so my radiuses that I would be drawing, there's a radius there. Here's another radius here, right? That was just a typical radius. Here's another radius. I've broken my pencil with my aggression. And here's a radius. And how many radiuses am I going to have? Well, I'd like to have infinitely many radiuses, right? And where are all of those radiuses going to be? They're going to be from y is 0 to y is 4. So that's my integral is going to go from y is 0 to y is 4. I'm going to be adding up all of these different size, right? They're going to get bigger and bigger, different size, wafer thin, trying to center it there, wafer thin discs, right? And I'm going to add them all up. And when y is 0, I have a disc of size 0. And when y is 1, here's my formula, there, I have a disc of size 1/2 squared, 1/4 pi, right, is the size of my disc at that point. And my discs are going to go all the way from 0 to 4, and there's going to be infinitely many of them. And so now all I have to do is integrate this, and this shape, oh my gosh, you guys will probably be better at drawing them than I am in 3D, and so that's why I refer to the Professor Bob. He's really good at drawing them. And so the pi over 4 just stays still. And so when I take the antiderivative, I'm going to get pi over 4 times, and then the antiderivative of y to the 4th, which is y to the 5th over 5, from 0 to 4. So the volume equals pi over 4 times 4 to the 5th over 5 minus pi over 4 times 0 to the 5th over 5, which this is just 0. And 4 to the 5th is big. I don't know what it is. Do you know what it is? So I'm going to divide that by 20. So I'm getting the volume here is 256 pi over 5 is what I'm getting. So we did a lovely job on that. And so I just did 4 to the 5th divided by 20. If you were clever, if I was clever, I could have done 4 to the 3rd divided by 5, right? And so there we found the volume there. Okay, so that was an example of going around the x-axis and going around the y-axis. In our next video, we'll do an example of going around something different. So